In section 2.2, we're going to look at what's called vertical and horizontal shifts. So we're just going to take graphs and we're going to move them vertically up and down and horizontally left and right. First thing we're going to look at is we're going to look at our vertical shifts. Sometimes these shifts are called translations. So your book may use this word translation. And a translation is simply taking a graph and moving it left, right, or up and down. It doesn't change the shape of the graph. So a translation is actually a type of transformation. A transformation will take a graph and it will change its position or shape. So it could do a translation, move left, right, up, down, or it could stretch the graph out or shrink the graph in. In the case that we're stretching or shrinking a graph, that is not a translation. That is a different type of transformation. So oftentimes I will, instead of using translation, I'll just say transformation because a translation is a type of transformation. Regardless, let's look at our vertical shift or vertical translation. So when we think vertical, we should think vertical line, think the y-axis. When we shift a graph vertically, what we're doing is we're changing the y value. So if we shift up, which would be this first shift, that would be adding some value to the y. Notice that the function f of x has already done its job. It remains the same. That plus c is just adding to the y value. So that would be up on the y-axis direction. Now, if we subtract a value, function remains the same. We're subtracting from the y value. That would be a shift down. So these should make sense. What we're going to do is just look at a specific example using specific basic functions or parent functions. We're going to look at our square root function, y equal to the square root of x. So just to note, our f of x is equal to this square root of x. Now what I'm going to do is I'm just going to plot some points. So we're going to work across the first row and then we'll graph this. If x is 0, y is 0. If x is 1, y is 1. If x is 4, y is 2. So looking at this first graph below, y equal to the square root of x, if I plot those points, it's going to go through 0, 0, 1, 1, and 4, 2. And this would be the graph that we had seen in our prior section, 2.1, of the square root of x. So what happens if I add 2? Notice my f of x, square root of x, did not change. Function already did its job. That plus 2 is just going to go to the y value. So that should be a shift up on the y-axis 2 units. So let's put in 0 for x and plot some points. That would be 2 for y. If I put in 1 for x, that would be 3 for my y. And if I put in 4 for x, I would have 4 for my y. So now let's just look and compare these two columns and look at those ordered pairs. Notice that what I did here is I changed the y value by adding 2. So if you look at the ordered pair, we went from a 0 to a 2 because all we're doing is adding 2 to the y value. Then we went from a 1 to a 3 because we're just adding 2 to the y value, and then a 2 to a 4. So this translation or transformation, it makes sense. Now let's go ahead and graph this in our second graph, y equal to the square root of x plus 2. And we'll plot those points. We have 0, 2, 1, 3, and 4, 4. The graph did exactly what I expected it to do. It took my original graph and it shifted it up 2 units. what I'm going to do now is I'm going to take that shifted graph and I'm going to go back to the very first graph. And remember what we did. We added 2 to our y value. So that would be simply adding 2 to the point 0, 0. It becomes 0, 2. And then the next point where the y value is 1, if we add 2, we get 3. So I'm just taking this graph and I'm shifting it up 2 units. Okay? The y value of 2 goes up 2 units to 4. So whenever you have a transformation, you can take your parent or your basic graph and you can just shift it around, or you can plot points. So in the first example, when we were putting in ordered pairs in our rows, we were plotting points. In the second example, where you see how I graph the red graph, the translated graph above y is equal to square root of x, that would be using the transformation or the translation and just moving our basic or parent graph up 2 units. So if we look at this last case where we're subtracting 2, function stays the same. So subtracting 2 from the y values, it's going to do exactly what we expect. It's going to go down 2 units. If I put in 0 for x, I get negative 2. 1 for x, I get negative 1 for y. 4 for x, I get 0. So remember, this is with respect to our original basic graph, y is equal to the square root of x. What we're doing is we're taking the y value 0 and we're subtracting 2 to get a negative 2. Taking the y value of 1, subtracting 2 to get a negative 1. Taking the y value of 2, subtracting 2 to get 0. Graphing in the last coordinate system, if I graph the point 0, negative 2, 1, negative 1, and 4, 0, I've taken that original graph and shifted it down 2 units. So let's go back to our y is equal to the square root of x. If I simply go down 2 units, from each of these points, down, 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 I get my vertical shift down. Let's move on to a horizontal shift. So when we talk about horizontal shifts, you should be thinking of a horizontal line, which would be our x-axis. So this time we're changing our x values. And that's why when you look at the description, the first one is y equal to f of, in parentheses, x minus c. So we're subtracting some real number c from the x values before the function has done its job. That's actually opposite of what you think should happen. Intuitively, we think, okay, well, if we're subtracting from the x, does that mean we're going to be moving to the left in the negative direction on the x-axis? And the answer is no. We're doing the actual opposite. Whenever you subtract from your x, it's actually going to be a shift right. And when you add to the x, it's a shift left. So it's opposite of what you think will actually happen. Again, let's go look at a specific example. This time we're going to look at our absolute value function, y equal to absolute value of x. And we're just going to plot some points, graph our basic or parent function, and then we're going to graph the transformations or the translations. So if x is 0, y is 0. If x is 2, y is 2. Negative 2 gives me a positive 2 for y. 3 is 3. Negative 3 is 3. Looking at this first graph, y equal to the absolute value of x, it's going to pass through 0, 0, 2, 2. The next one was negative 2, 2. Oops. And we have 3, 3, negative 3, positive 3. Graphing this function gives us our basic absolute value graph. The next thing we're going to do on the next row is we're going to subtract 2 from the x value before the absolute value function has done its job. So now if I put in 0 for x, I get the absolute value of -2, which is 2 for my y value. Put in 2, absolute value of 0 is 0. Put in -2, absolute value of -4 is +4. Put in 3, I get absolute value of 1, which is +1. Put in -3, absolute value of -5 is +5. Plotting those points on our second graph, remember the minus means a shift right. I'm expecting this graph to shift right 2 units. I have 0, 2, 2, 0, -2, 4, 3, 1, and -3, +5. And you can go ahead and plot more points if you would like, perhaps putting in some more positive x values. But what we see is that we have shifted over 2 units to the right. The last graph, y equal to the absolute value of x plus 2. So adding to the x actually means a shift to the left. Plot points, put in 0, y value of 2, put in 2, y value is 4, put in -2, y value is 0, put in 3, the y value is 5, and then put in -3, our y value is 1. Graphing that, it'll pass through 0, 2, 2, 4, -2, 0, 3, 5, -3, 1. Again, you can plot more points, maybe put in some more negative x values, and you'll see that this is going to be a shift to the left 2 units. So let's go back to our parent graph and then just use the transformation instead of plotting points. So I have some key points here. If I was going to graph y equal to the absolute value of x minus 2, that would be 2 units right. So I'm just going to take my points and move them over 2 units to the right. So that's one side of this absolute value graph. And then continue on, 2 to the right, 2 to the right. I get the rest. So this would be our y equal to the absolute value of x minus 2. If I take that original graph and I add 2 to the x, that's going to be a shift left 2 units. So I can just go left 2, left 2, left 2, left 2, left 2. And then just using the transformation, I get y equal to the absolute value of x minus 2, or x plus 2. Sorry, x plus 2. Okay, so those are the 2 translations that we're doing in this section. It's going to be up, down, left, right. So now what we're going to do is we're going to practice going from words to equation, equation to words. In example 1, it says to write an equation in x and y that results in the desired translation. So we're given a description of an equation in words. We're going to translate that to an equation using math symbols. Part A, the cubing function shifted 4 units upward. First of all, cubing function. It's not the cube root, which would be the radical. It is cubing function, which is x to the third. And then since we're shifting 4 units upward, that means we're adding 4. Thus, it's going to be y equal to x to the third plus 4. Try this again. Part B. the absolute value function. So the absolute value function is absolute value of x. And we're going to shift it 7 units to the left. So left, right means you're changing the x value. You're changing within the absolute values. To the left means you're actually adding 7, which gives us y equal to the absolute value of x plus 7. And another one. Part C, the square root function shifted 12 units downward and 5 units to the right. So there's actually 2 translations going on here. We're starting out with our square root function, which is simply the square root of x. 12 units downward, up, down is you're changing the y value, so downward is a minus 12. But 5 units to the right, that's changing your x. And right actually means negative. So we're minusing 5. We get y equal to the square root of, we're changing the x by subtracting 5 because it's to the right. But then we're going down, so outside of the square root function, we're going to subtract 12. Last one, we're looking at the squaring function. So squaring function is x squared, shifted 1 unit up, so up would be a plus 1. 45 units to the left would mean we're actually adding 45. Y equal to, now the plus 45 is to the left, we're changing the x value, so parenthesis x plus 45 squared, and then we're adding 1. So now that we've gone from words to equations, let's go the other way from an equation to words. In example 2, we want to describe the translation from our function f to our function g. Part A, g of x is equal to f of x plus 7. So here we're adding 7 to the x value, which is, remember, it's going to be a translation left or right, but since we're adding 7, it's going to be left. So this is just a shift left 7 units. Part B, g of x is equal to f of x minus 11. So notice that we're subtracting 11, but whatever this function is, it remained unchanged. So the minus 11 on the outside is changing our y value, and since it's a minus, it would be down. This is a shift downward, or you could just say down by 11 units. And another one. Part C is actually 2 translations because notice that we are subtracting 4 from the x. So minusing on the x would be right. And then we're adding on the outside of the function the 3/4. So we're adding to the y value and it's a plus, so it would be up. So we're going to go right and up. Now, I typically do my descriptions in the order of operations, meaning I work within my parentheses and I describe my x. So my left, right first, and then the plus 3/4 would be the up, down. I'll do that second. But technically with translations, order doesn't matter. So I'm going to describe my shift, and I'm going to do the x. The minus 4 would be a right, so I'm going to shift right 4 units, and the plus 3/4 would be up by 3/4 units. Okay, let's try this again in part D. G of x is equal to f of x plus 1.5 minus 5.99. The plus on the x means a shift left. So I'm going to shift left 1.5 units, and the minus would be down, and down 5.99 units. The last thing we're going to do in this section is just transformations, not by plotting points, but instead taking our basic or our parent function and moving it around. Oh, very noisy chickens. Example 3, we want to sketch the graph of the function, not by plotting points, but by starting with the graph of a basic or parent function, and then applying our transformation. In this case, the transformations are translations. We're also going to state the domain and the range of the function. So think about this in general. If you're shifting a graph up and down, you're changing your y values, so it may affect your range. If your translation is left to right, you're changing your x values, so that could affect your domain. In the case where the domain or range is negative to positive infinity, the translations will not change the domain and range. You'll still get negative to positive infinity. But if you do have a restricted domain or a smaller domain than negative to positive infinity, or a smaller range than negative to positive infinity, these translations will affect your domain and range. Let's look at part A. So the first thing I want to do with y equal to x squared minus 3 is to state my parent function, because that's what I'm going to graph. And my parent function is y equal to x squared. I am going to do a few points. So it's going to pass through 0, 0, 1, 1. If I put in 2 for x, I get 4. If I put in negative 1, I get a positive 1. Negative 2 gives me a positive 4. And this is simply a parabola. So maybe I'm going to, do it with a different color, but maybe I'll just do the final graph in black and label it. So this is my parent function, x squared. Domain is all real numbers. My range is restricted. Notice the first y value I have is a y value of 0. So my range for this parent function is 0 to infinity, and I would include 0. Since I'm going to be subtracting 3, but the x squared, the parent function, remains the same, that tells me I'm going to shift down 3 units. I'm changing my y value. Since I started out with a restricted or smaller range, my range will change. Let's go ahead and graph this. Shift down 3 means I'm going to take my graph and I'm going to shift it down 3. So maybe I will show the shift in a lighter color, 1, 2, 3, and then graph 1, 2, 3 in a darker color. So I have these key points that I'm going to use to do my final graph. Oh, that's a sad graph. Okay, so this is y equal to x squared minus 3 using the transformation. When I look at the domain, it did not change. It's still all real numbers. So negative to positive infinity, but my range did change. The first y value I get is here at negative 3. And then I get all the other y values. So it's going to go up to positive infinity. So again, the shift down changed my range. Let's try this again in part B. Again, the parent function here is still our squaring function, x squared. I'm changing the x value within the parentheses. So if you just take away that minus 2, you end up with y equal to x squared. Same graph as I had in the first one, 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, and I have my parent. So the minus 2 within the parentheses means I'm going to shift right 2 units. So I'm going to take all these points and I'm going to shift them right 2. And my graph will be this parabola or this squaring function shifted. Now I changed my x value, however my original domain was all real numbers. So since my original domain was all real numbers, shifting left right is not going to change my domain. It's still going to be negative infinity to positive infinity. And the range for this particular parabola, if it was just an x squared, would have been 0 to positive infinity. Shift left and right did not change my y values. My first y value is still 0. And then I go to positive infinity. We'll do 2 more examples and then that will be it for this section. C is y equal to the absolute value of x minus 1 plus 2. So if I take away that plus 2 and I take away the minus 1, I'm left with my parent or basic graph y equal to absolute value of x. So this is the absolute value function. I could put in anything for x, so the domain is negative infinity to positive infinity, but the y values will always be 0 or some positive number. So the range for the absolute value graph is going to be 0 to positive infinity. So if I do any right, left, change the x, my domain will still be negative to positive infinity. But if I do any shift up and down, that'll change my range. Let's go ahead and graph our basic or parent graph. Absolute value passes through 0, 0, and I'll just do it by 2s. It'll go through 2, 2, and 4, 4, and then negative 2, positive 2, negative 4, positive 4. And I have my basic or parent graph. So what order should I do these translations since I have 2 of them? Well, whenever you have translations up, down, left, right, the order really doesn't matter. However, for some transformations, order does matter. Not with translations, but other translations, order matters. So to be safe, we typically go by order of operations. Imagine if you were to put in an x value. The first thing you would do is you would minus 1. So I'm going to do the translations left, right first, and then do anything outside the absolute value function, which would be the plus 2 last. So I'm going to take this absolute value function, and the minus 1 means I'm going to go right 1 unit. So I'm going to move all of these points 1 to the right to get my first transformation, which is a translation 1 unit to the right. The next thing I'm going to do is the plus 2. The plus 2 would be up 2 units, which means I'm going to go up from here 2 units, 2 units, 2 units for each one of the points on the green graph. I will graph this in black so we could see that this would be y equal to the absolute value of x minus 1 and then plus 2. And domain and range. So, domain did not change. It was all real numbers or negative to positive infinity. It's still negative to positive infinity. Our range did change. The first y value I have is at positive 2 because of that plus 2 to the y values. So my range is going to be a bracket because I include 2, and then we go to positive infinity. Last example, we're going to look at the square root of x plus 3 minus 2. So if I take away the plus 3 minus 2, my parent or basic graph would be the square root function, square root of x. So typically we start out with x is equal to 0, and then we'll do some nice numbers. So 1 is a perfect square, 4 is a perfect square, and I end up with 4, 2. And I have my parent graph. So the plus 3 underneath the square root means I'm going to move to the left 3 units. I am going to just move all of these 1, 2, 3, 1, 2, 3 to the left, 1, 2, 3. And then the minus 2 means I'm going to go down with the green graph 3 units. I'm just going to use black for this. So if I go, or 2 units, go down 2 units, go down 2 units, and then go down 2 units, I have my translated graph. If you were graphing by hand and you didn't have a nice graph with nice points, you would definitely have to label some points. And it's a good idea to label points anyway. However, the domain of my original parent graph was restricted. The original domain, I'll just do, was 0 to infinity, and the original range was also 0 to infinity. So x values 0 and anything positive, y values you get 0 and anything positive. So since I did a shift of plus 3 to the left, notice that my first x value is actually negative 3. It's opposite of what you do. So the domain for my translated would be how I changed my x. It was to the left 3 units. That means it's going to be a negative 3. And you could just look at the graph. This first point is x is negative 3. The y value is negative 2. So the graph starts with an x value of negative 3, but it goes on to positive infinity. And the range as well, since I went down 2 units, I'm going to subtract 2 from my y value. My range originally started with 0, so it's going to start now at negative 2. And you can see from the graph, the first y value you get is a y value of negative 2. Our range is going to be negative 2 to positive infinity. And that's it for this section.